For a lot of you, this week's material is going to be a new experience. We're going to expose you to something that you probably haven't seen before. And so I've tried to put together a few diagrams to help ease that transition from what you know to what you don't. And hopefully these videos will help explain these diagrams to you. In front of you right now is an image that has two diagrams in it. They both have the title Sequential Code above them, and that's because they both are code sequences. They are code sequences that you have actually written before, and we're going to take a look at these and make sure everybody understands exactly the sequence in which code will be executing in these two situations. The diagram on the left represents conditional branching. In languages that you've used in the past, you probably implemented this conditional branching using something like an if-else statement or an if, else if, else statement. We're going to keep it simple, just if and else if. In Erlang, this is done with pattern matching, so it'll be a little different. But they are the same idea, and it's conditional branching. I have a solid line, and I have a dotted line. And you can see they meet at the top, and it says branch here. That's where your if statement would be or your pattern matching would be. And the code will go one way or the other. I've represented the direction the code is executing with a solid line, and the dotted line represents the branch that was not chosen. So they branch up there where it says branch here, and after they are done, both paths recombine at where it says recombine here. That would be the line of code you wrote that was after your if and your else clauses. So that is very sequential. There's no jumping around. The code is just built to run one thing right after another. And so that's something you should be very used to. Hopefully you understand that it is one step after another. There isn't jumping around. On the right, you'll see something that's related to the conditional branching of if, else, and pattern matching, but is a little different. It is still conditional branching, but it's going to be a loop in something like Python or recursion in Erlang. You'll notice that branch and recombine here is at a single point. It's that little pointy spot of that weird four-sided figure. And that is literally what is going to happen. You're going to not skip stuff. Sometimes people think, oh, I'm going to go over skip, and then I'm going to skip down to the end of my loop. That's not how things happen. Your loop is there and it's busy executing. The line, when you sequentially are doing things, the while statement is directly followed by the next line of code after your loop. So there isn't any jumping out and doing things. It's all happening in the same execution space. Okay, so no jumping around here. Now we're going to take a look at something that is dramatically different. This is not going to be sequential code. We're going to be talking about concurrent code. Your computer has more than one core. It can do more than one thing at the same time. Just like you and your friends can all do different things at the same time. If there were 4 of you, each of you could be doing something different. So 4 things would be being done at the same time. Your computer works the same way. And in fact, all modern applications leverage this a lot. And Erlang happens to be really good at leveraging this ability of your computer to do multiple things at the same time. We're going to start with the one on the right, because this is the one that will be the most familiar to you, the one that you're probably going to be the most comfortable with, the one that most people who are new to this are comfortable with. So let's talk about that situation. So again, you can see on the right where it says branch here and recombine here. And then you'll see 1, 2, 3, 4, 5, 6, 7 lines in between those two spots. That's where this code is doing 7 different things at the same time. And you can see right by the side it says compute stuff here. So what's happening is we have one line of execution happening. It hits the branch here spot and it breaks up into 7 different things happening at the same time. And then when all of those get done, it recombines into, once again, a single sequential bunch of stuff to do. So it starts off sequential, breaks into concurrent, and then becomes sequential again. Okay, that would be like, you go do this part of the assignment, I'll go do this part of the assignment, and they'll go do that part of the assignment. And when we're all done, we'll bring the parts together and combine them. Okay, so that would be a real life example of this. This is the kind of concurrent and parallel programming that happens when you use a GPU. Many of you probably don't know what that is, and that's okay. That's okay. But this is one way that you can do concurrent programming. In the upper left, you'll see another way of doing concurrent programming, and you'll notice that we still have that single concurrent line and it hits the branching point, but here it doesn't ever recombine. It just stays branched. Okay, now this is hard for a lot of people to think about, and that's okay if it's a hard for you to think about. Let me give you an example. You have a multiplayer game that you're playing on your phone. The other players are each doing their own thing, and you're doing your own thing, and there is no requirement that you all meet up at the end. Each of you can be running off and doing your own thing. This is a really good way of writing concurrent code. On the bottom left is another example of good concurrent code. And here you can see we've got some sort of looping kind of a thing going on. It's not a loop, so don't worry about that. We don't need to use that word, but I don't have another word to deal with this. A recurring thing going on. That's better. We have a recurring thing going on. And what's happening is in that loop, that is some recurring calculation. It's not a loop, but it's waiting for a trigger. It's not actually doing any execution. It's just sitting there waiting for something to happen. And then the trigger happens. Somebody clicks a button or somebody logs in or whatever, joins a game, whatever that trigger is. And when that trigger happens, you can see there's that right angle-y line of execution of some code, and it goes off and it never recombines. And in the meantime, the roundy recurring thing goes back to waiting for another trigger. Okay, now that may take some thinking, because you're used to thinking of code runs until you get to the end of the code. But there are ways that you can put waits. I want you to keep running until you get to here and then wait for a trigger. And then when the trigger happens, keep going. All right, so that's what's being represented here. An example in the real world of this may be you're on your phone and you're on your web browser and you click a link and you're going to a web server. That's what's happening. You're actually making a request of a web server, and the web server will create a special separate code execution for dealing with your request, and then it will go back around and wait for somebody else to make a request. And when they make a request, it'll make a separate bit of code go off and execute for that person at the same time as it's working on yours, and it'll go back to waiting. And that way, web servers don't have to wait until you're done receiving your stuff before it can help somebody else with their request. You'll notice that at the top, on the left, it says good concurrent code, and on the right, it says not so good concurrent code. Most people, when they're new to this, tend to try to write all of their stuff and design and engineer all of their stuff so it works like the diagram on the right. When you get really good at engineering this stuff, you will write a lot more stuff that looks like the two options on the left. Why is the left better than the right? Because on the right, you have a bottleneck. You have a bottleneck where you have to wait for all of those things to recombine. And that's going to slow down your code and slow down what's happening in your application since it has to wait there. While we do have a waiting for a trigger here, that's because there's nothing for the application to do at that point. Instead of waiting to do something else once all of that other concurrent stuff gets done. So on the right, it's wait to do a bunch of stuff until all the concurrency is done. On the bottom left, it's there isn't anything for me to do until the trigger happens. Then I can spin off some work to be done and come back and wait again. So engineers that really, really get good at this think on the left-hand side first, and if there happens to be some edge case where they cannot do it on the left, like we see on the left, they will revert to doing it on the right. Whereas most people new to it tend to do it on the right and wait to be forced to do it on the left by some engineer that knows more about it than they do. So that's why it's labeled good current code and not so good current code. It's not bad, it's just not as good as the other way if we can make it happen.